Welcome, everyone. In this explainer, we're diving headfirst into one of the most extreme, mysterious, and frankly, coolest objects in the entire universe, the black hole.
Okay, so when you picture a black hole, what's the first thing that pops into your head? Probably some kind of giant cosmic vacuum cleaner, right? Just hoovering up everything in its path. Well, today, we're going to challenge that idea and ask, what if it's less of a vacuum and more of a powerful cosmic engine?
You see, the popular myth is that black holes are literally empty holes punched in the fabric of space, but the reality is, well, it's the complete opposite. They aren't empty at all. They are regions where a truly staggering amount of matter has been crushed into an impossibly small space, creating an object with just overwhelming gravity.
To really get a grip on that gravity, we have to start right at its edge. So our first stop on this journey is the boundary that really defines what a black hole is.
That boundary has a really cool name, the event horizon. And you can think of it as the universe's ultimate one-way door. Once you cross this line, there's absolutely no coming back. Not even for light, the fastest thing we know of.
But here is where your brain starts to melt a little. The event horizon isn't a physical surface you could, touch or stand on. It's a boundary that's actually woven into the fabric of space-time itself. It's just a point in space where gravity gets so intense that the speed you'd need to escape is faster than the speed of light. And since nothing can go that fast, well, you're stuck.
And this whole idea has been kicking around for a lot longer than you might think. The journey started way back in 1783 with this concept of dark stars, then it got its real mathematical power from Einstein's theories in 1915, and finally, it all culminated in 2019 when we captured the first ever image of a black hole's shadow. A 200-year leap from a pure thought experiment to an actual photograph. How incredible is that?
So it turns out not all black holes are created equal, not by a long shot. In fact, there's a whole variety of them out there. So let's take a quick tour through the cosmic zoo and meet the different species of these amazing gravitational monsters.
Here's our little field guide for the tour. First up, you've got your stellar mass black holes. These are the most common kind, born from the spectacular collapse of massive stars. Then we have the really elusive intermediate mass black holes. They're kind of the missing link we're still hunting for. After them, you get to the true giants, the supermassive black holes, the anchors sitting at the heart of nearly every galaxy. And finally, you have the hypothetical primordial black holes, which, if they exist, might be leftover relics from the Big Bang itself.
So let's try to get a sense of scale, starting with a pretty beefy stellar mass black hole. A recently discovered one, Gaia BH3, clocks in at 33 times the mass of our Sun. Pretty hefty, right? But believe me, we are just warming up. Okay, now let's jump up a few weight classes and look at the heart of our very own Milky Way galaxy. Meet Sagittarius A star. Its mass isn't 33 suns, it's 4 million times the mass of our Sun. The scale is already getting hard to picture.
But even that is just a baby compared to the true titans of the cosmos. At the heart of a galaxy called Holmberg 15A, we found an absolute monster with the mass of 40 billion suns. The numbers just start to feel meaningless at this point. It's staggering.
So, with that kind of insane mass, what actually happens when something gets a little too close? Let's zoom in on the action and see what fate awaits matter at the edge of this gravitational abyss.
For an unlucky star, it's basically a 4-act cosmic drama. First, that intense gravitational pulse starts to stretch it out. Second, these tidal forces become so extreme that they shred the star into a long noodle of plasma. And yes, scientists really officially call this process spaghettification. You gotta love it. Third, all that stellar debris gets whipped into a superheated, glowing whirlpool called an accretion disk. And finally, from all that chaos, powerful jets of energy can launch from the poles at nearly the speed of light.
And here is a fantastic irony. The black hole itself is, of course, invisible, the definition of darkness. But this violent process of consumption, that glowing, superheated accretion disk, can make its immediate neighborhood one of the absolute brightest sources of light in the entire universe.
And this right here brings us all the way back to our opening question. These incredibly powerful relativistic jets can sculpt and influence entire galaxies. This proves that active black holes are not just passive consumers. No way. They are tremendously powerful cosmic engines, recycling matter and blasting out incredible amounts of energy across the cosmos.
Now, all this talk of spaghettification and consumption and cosmic engines naturally leads to a very human question. Are we in any danger here?
The short answer is a very definite no. This number you see, 1,560 light-years, is the distance to Gaia BH1, the closest known black hole to us. That is an immense, almost unimaginable distance. Space is vast, and that vastness is our greatest shield.
And let's really hammer this point home, because it's important. Gravity is gravity. From a safe distance, a black hole's pull is no different than any other object of the same mass. If our sun were magically replaced by a black hole of the exact same mass, Earth would just keep orbiting it like nothing happened. We'd just be very, very cold and in the dark. So, that whole cosmic vacuum cleaner myth, it's officially busted.
Okay, so black holes might consume stars, but what about their own ultimate fate? Do they last forever? Well, to answer that, we have to look deep, deep into the future of the cosmos.
So in one of the most brilliant insights of modern physics, the legendary Stephen Hawking predicted that black holes aren't actually eternal. Because of some really bizarre quantum effects happening right at the event horizon, they should leak a tiny amount of energy. It's called Hawking radiation, and it means they slowly, and I mean very slowly, evaporate over time. And the timescale for this evaporation is just, well, it breaks your brain. A single stellar mass black hole will take 10 to the power of 67 years to fade away. A supermassive one could take 10 to the 100th. They will long, long outlive every single star, becoming the very last massive objects in a cold, dark universe.
And this really gets to the very heart of why we're so fascinated by them. They aren't just objects. They are the universe's ultimate laboratories. They're places where the laws of physics as we know them are pushed to their absolute breaking points, and they might just point the way toward a deeper understanding of everything.
So this leaves us with a final thought to chew on. We tend to see black holes as an ending, the final stop for matter and light. But if they're the very last things to exist, slowly radiating their mass back into the void long after everything else is gone, are they truly an end, or are they something else entirely? The universe's final, patient glow. It's an incredible idea to think about. Thank you for joining this explainer.